In this video lesson, we're going to take you through an overview of ionic bonding. Starting with the question, what is a bond? Right? A bond is a chemical force holding atoms together. And they can come in this chemical force can happen in a variety of ways, and so we're going to explore each one of these in the next 2 units. This unit we're going to focus on ionic bonding and metallic bonding. And in the next unit we'll be focusing on covalent bonding. So there's different ways that chemical force can happen. It all depends on electrons and the atoms that are participating in the bonding experience, and how strong each one of those atoms is holding on to its electrons. So ionic bonding, let's talk a little bit more about that. Ionic bonding is essentially when you have oppositely charged particles which we are calling ions. When you have those oppositely charged particles, a cation and an anion, the positive ion and a negative ion, when those oppositely charged particles attract. It's the attraction of the oppositely charged particles. So here we see a sodium atom. Overall, it is a +1 charge, right? So this is the cation. This chloride ion is overall negatively charged. This is the anion. And it is this attraction of the cation to the anion that is the ionic bond. Okay, why is this positively charged? Well, sodium ions have 11 protons, but if you count up the number of electrons, there are 10 electrons. So overall, this is a +1 charge. Chlorine has 17 protons. And if you count up the number of electrons here, it is 18 electrons. So overall, it's a -1 charge. Okay, and it is that oppositely charged particles attracting that is the ionic bond. Sometimes that attraction of oppositely charged particles is known as the electrostatic attraction. Well, ionic bonds typically form between metals and nonmetals. And if we consider this periodic table, the metals we are talking about, or the nonmetals we're talking about, are basically everybody over here, right? Not really the noble gases, because they are typically satisfied and don't need to be sharing, or they already have a full valence shell. So these are our nonmetals. It also includes this hydrogen right here. Okay. And then the metals are basically just about every other element with the exception of the metalloids. Right? So everybody down here. And I'm just going to kind of go essentially here, these are the metals. And of course the metalloids are, we're not going to really address them too much in this unit because they tend to not participate in ionic bonding, although they can. And because of that lack of commitment, we're going to ignore them in this particular unit. Okay, so metals, right? Metals, what do we know about metals? This a little bit. Metals have low ionization energy and electronegativity. Right? We know this about metals. What that means is that they are going to lose electrons. Remember, this is the process known as oxidation. And metals typically become cations, because that's what happens when they lose their valence electrons. they have fewer electrons than protons, and overall they are charged. So cation, they become positively charged ions. The nonmetals have a high ionization energy and electronegativity. And so they are more likely to gain electrons through a process known as reduction. And when they gain those electrons, they become anions, which of course are negatively charged ions. Okay. So because metals become cations and nonmetals become anions, you typically need a cation and anion to have that oppositely charged electrostatic attraction. So we typically say with the general rule that ionic bonds form between metals and nonmetals. All right, so let's take a look at the back side. Now when ions form in their solid phase, right, when they're solids, we say that they form a structure known as a crystal lattice. You may have seen a lattice like in a garden, so it's this regularly repeating pattern, and they tend to form beautiful crystals with many different faces, right? And so that is because of the way that the ions are kind of very orderly, kind of stacking together. If we take a look at an example here, sodium chloride, there's our metal, there's our nonmetal, so this is ionic. We are going to see what it's really made up of are sodium ions and chloride ions. So the sodium becomes a +1, the chloride becomes a -1. And then they're going to stack, right? And so in this case, the anions are larger, so I'm going to put a negative charge in each one of those, and the cations are smaller. I'm going to put a positively charged ion there. So you can see that every positive charge is surrounded by a negative, and every negative charge is surrounded by a positive. So this is why ionic solids are quite stable. They are, every charged particle is surrounded by oppositely charged particles, and they just kind of all nestle and snuggle together quite nicely. Okay. So why is this formula just NaCl? That's a 1-to-1 ratio, where if we counted them up, if you count up all the positive ions here, there are 9 sodiums, and if you count up the chlorines, there are 9 of those. Okay, so ionic formulas don't represent the actual number. The ionic formulas represent the lowest reduced ratio. So we wouldn't write this as Na9Cl9, we would just write this as NaCl, which is a 1-to-1 ratio. Now, other crystal structures can form differently. This is just as an example. This one here is sodium chloride. This is calcium chloride. Because of the way the ions can stack differently, you will end up with different shapes of crystals that you can hold in your hand, and they become multifaceted. But the structure of the crystal that you would hold in your hand is based very much on the internal structure of the ions. And so that's just there to remind you that not all ionic crystal structures are like the sodium chloride, although this is the one that's typically shown to you because it's such a common example. So what we were just talking about, the ionic compound formulas are always the lowest ratio of cations and anions. This is, when we say the lowest ratio, this is what is known as an empirical formula. An empirical formula. An empirical formula is a chemical formula showing the simplest ratio of elements in compound rather than the actual number of atoms. All right, and so ionic compound formulas are always going to be an empirical formula. Ionic compounds do not exist as independent, distinct particles, so we cannot call them molecules. And instead, we refer to their chemical formulas as formula units. All right, so this concludes our lesson that is an overview of ionic bonding. Stay tuned for the next video lesson, and otherwise I will see you back in the classroom.